Space looks peaceful from here, doesn't it? That's how it kills you. Quietly, beautifully, without warning. You're 40 trillion kilometers from home, bound for Alpha Centauri, surrounded by darkness so complete it feels like meditation. The sun is a memory, the destination is a promise, and between them stretches the most hostile environment in existence. If you want to explore the biggest mysteries of our universe, make sure to subscribe to this channel. Now let's get started. Let's talk about Alpha Centauri for a moment, because understanding your destination helps you grasp just how monumental this challenge really is. Alpha Centauri isn't actually one star, it's three. Alpha Centauri A and B form a binary pair, two sun-like stars locked in an eternal gravitational dance around each other. Then there's Proxima Centauri, a small red dwarf that orbits the other two at a tremendous distance. Proxima is actually the closest of the three to us, sitting at about 4.24 light-years away. To put that in perspective, Voyager 1, humanity's most distant spacecraft, launched in 1977 and has been traveling for nearly 50 years. It's currently moving at about 17 kilometers per second relative to the Sun. That sounds fast until you realize it would take Voyager 1 over 73,000 years to reach Proxima Centauri if it were headed in that direction, which it's not. But let's say we don't want to wait 73 millennia. Let's say we develop technology that can push a crude spacecraft to 10% the speed of light. That's still an absolutely blistering 30,000 kilometers per second. Even at that speed, the journey takes over 43 years. That's longer than most careers. That's potentially an entire adult lifetime spent in a metal can hurtling through the void. And during every single one of those 43 years, space is actively trying to end you. You might think space is empty. After all, when you look up at night, you see a whole lot of nothing between those points of light. We even call it the vacuum of space. But here's what modern astronomy has taught us. Space is anything but empty. It's filled with particles, radiation, magnetic fields, dust, debris, and energies we're only beginning to understand. The interstellar medium, as scientists call it, is a thin soup of hydrogen atoms, cosmic dust grains, and wandering molecules spread across the galaxy. On average, there's about 1 atom per cubic centimeter out there. That doesn't sound like much, and compared to Earth's atmosphere, with its 10 to the 19th power molecules per cubic centimeter, it's practically nothing. But when you're traveling at 10% the speed of light, even that near-nothingness becomes a hazard. Think about it this way. You're moving so fast that from your spacecraft's perspective, the interstellar medium isn't drifting lazily past you. It's slamming into your hull like a relentless sandblaster made of atomic particles. Every hydrogen atom, every speck of dust becomes a high-energy projectile. The faster you go, the more violent each collision becomes. At relativistic speeds, which means a significant fraction of light speed, these impacts release tremendous energy. Scientists studying concepts like breakthrough starshot, a proposal to send tiny light sail probes to Alpha Centauri at 20% light speed, have calculated the damage these collisions would cause. When a spacecraft moving at that velocity hits even a single grain of dust 1/10 of a millimeter across, the impact energy equals getting hit by an exploding hand grenade, a grain of dust. Imagine what happens if you hit something bigger. Your spacecraft needs shielding, serious shielding, to survive this onslaught. But here's the cruel irony. The more shielding you add, the heavier your ship becomes. The heavier your ship, the more energy you need to accelerate it to interstellar speeds. The more energy you need, the more fuel you carry, or the more power your propulsion system requires. It's a vicious cycle that makes engineering an interstellar spacecraft one of the hardest problems humanity has ever faced. But let's say you solve that. Let's say you design a hull with layered shielding, maybe a Whipple shield, which uses multiple thin layers to vaporize incoming particles before they penetrate. You've protected yourself from dust impacts. Problem solved, right? Not even close, because now we need to talk about radiation, and this is where things get genuinely terrifying. Space radiation is invisible, silent, and absolutely relentless. Unlike the dangers you can see coming like asteroids or equipment malfunctions, radiation just seeps into you, atom by atom, breaking molecular bonds, shredding DNA, and fundamentally damaging the biological machinery that keeps you alive. There's no alarm that goes off when you're being irradiated at dangerous levels. You don't feel it happening. But it's happening every second of every day. On Earth, we're protected from the worst of space radiation by two incredible shields: our planet's magnetic field and its thick atmosphere. The magnetosphere deflects charged particles from the solar wind and cosmic rays, sending them spiraling along magnetic field lines toward the poles, where they create the beautiful auroras. The atmosphere absorbs what gets through, scattering and stopping high-energy particles before they reach the surface. In space, you have none of that. Let's break down the different types of radiation you'd face on an interstellar journey. First, there's solar radiation. The sun constantly emits a stream of charged particles, mostly protons and electrons, called the solar wind. This wind blows outward through the solar system at speeds of about 400 kilometers per second. It's not incredibly dangerous by itself, but it's persistent. Then there are solar particle events, sometimes called solar storms. These happen when the sun releases massive bursts of energy through solar flares or coronal mass ejections. When that happens, billions of tons of plasma and charged particles erupt from the sun's surface and race through space. If you're caught in one of these storms without proper shielding, you could receive a lethal dose of radiation in hours. NASA's Artemis 1 mission, which flew an uncrewed Orion spacecraft around the Moon in 2022, carried sophisticated radiation detectors to measure exposure beyond Earth's protective bubble. The data showed that even inside the heavily shielded Orion capsule, radiation levels were significantly higher than on the International Space Station. During passes through Earth's proton radiation belts, the Van Allen belts, dose rates spiked dramatically. In one test, changing the spacecraft's orientation reduced radiation exposure by about 50%, showing that shielding direction matters enormously. Now imagine you're not just passing through the Van Allen belts for a few hours. Imagine you're spending decades in deep space with no planetary magnetic field to help you. But solar radiation, as dangerous as it is, isn't even the worst of it. The real nightmare is galactic cosmic rays. Galactic cosmic rays, or GCRs, are high-energy particles that come from outside our solar system. They're born in some of the universe's most violent events: supernova explosions, colliding neutron stars, matter falling into black holes, and possibly even more exotic phenomena we don't fully understand yet. These particles, mostly protons, but also heavier atomic nuclei like helium, carbon, and iron, have been accelerated to nearly the speed of light. They carry staggering amounts of energy. When a galactic cosmic ray hits your spacecraft's hull, it doesn't just bounce off, it punches through. The heavier nuclei, especially iron nuclei, are particularly destructive. They can penetrate meters of shielding. When they pass through human tissue, they create tracks of ionization, ripping electrons off atoms and leaving a trail of chemical chaos in their wake. This damages DNA in ways that are much harder for cells to repair compared to ordinary radiation. A single heavy ion can slice through dozens of cells in a row like a microscopic bullet. The biological effects are deeply concerning. Radiation exposure increases cancer risk. That much we know from studying atomic bomb survivors and radiation workers here on Earth. But cosmic rays might cause other problems too. Studies on mice exposed to simulated space radiation show cognitive impairment, memory problems, and anxiety-like behavior. Some research suggests cosmic rays might damage the cardiovascular system, increasing the risk of heart disease. There's even evidence they could affect the central nervous system in ways that impair decision-making and reaction time, exactly the faculties you desperately need when piloting a spacecraft through the void. And here's the kicker: we don't fully understand the long-term effects yet, because no human has ever been exposed to deep space radiation for years on end. The Apollo astronauts who went to the moon spent only a few days in deep space. International Space Station crews orbit within Earth's magnetosphere, which still provides significant protection. A multi-decade voyage to Alpha Centauri would be uncharted territory for human biology. Speaking of which, if you're curious about the psychological and social dangers of spending lifetimes aboard a spacecraft, check out my video called "The Brutal Reason No One Survives: Generation Ships." It explores the human element of these impossibly long journeys, and trust me, the challenges go way beyond just the physics. It's on the card above and pinned on the comments. So how much radiation are we talking about? Scientists estimate that on a journey to Mars, which takes about 6 to 9 months, astronauts would receive a radiation dose of roughly 600 millisieverts. For comparison, the average person on Earth receives about 2 to 3 millisieverts per year from natural background radiation. A chest X-ray gives you about 0.1 millisieverts. 600 millisieverts significantly increases your lifetime cancer risk. Now scale that up to a 43-year journey to Alpha Centauri. Even with shielding, you're looking at cumulative doses that could reach tens of thousands of millisieverts, well into the range where acute radiation sickness, organ damage, and near-certain cancer become realities. Your bone marrow, which produces blood cells, would be under constant assault. Your immune system would weaken. Your eyes could develop cataracts. Your skin would age prematurely, and all of this assumes your shielding holds up for the entire journey. You might wonder why we can't just build thicker walls. More metal, more protection, right? Well, yes and no. Traditional shielding materials like aluminum or steel do block some radiation, but they also create a secondary problem called secondary radiation. When a high-energy cosmic ray slams into a heavy nucleus in your shielding, it can fragment both the cosmic ray and the shield material itself, creating a shower of secondary particles. Sometimes this secondary radiation can be even more dangerous than the original particle. Scientists have explored alternatives. Water is actually an excellent radiation shield because hydrogen atoms are effective at absorbing particle energy without creating as many dangerous secondaries. Some spacecraft designs propose surrounding crew quarters with water tanks serving double duty as both radiation shielding and life support storage. Polyethylene, a hydrogen-rich plastic, is another candidate. Some proposals even suggest using regolith, the rocky soil found on asteroids or moons, as bulk shielding material you could gather along the way. But here's the problem with all of these solutions: mass. Every kilogram of shielding is a kilogram you need to accelerate, decelerate, and carry across 40 trillion kilometers. The rocket equation, formulated by Konstantin Tsiolkovsky in the late 19th century, governs how much fuel you need to reach a given speed. And it's tyrannical. To go faster, you need more fuel, but more fuel adds mass, which means you need even more fuel to push that fuel, which adds more mass, and so on. It's exponential. Chemical rockets, the kind we use to launch satellites and reach the moon, are completely inadequate for interstellar travel. The fastest chemical rockets we've ever built, using gravity assists from planets, can barely reach 17 kilometers per second. That's only 0.0057% the speed of light. At that rate, you're looking at over 70,000 years to reach Alpha Centauri. Ion drives, which use electric fields to accelerate ions to high speeds, are more efficient but produce very low thrust. They're great for long-duration missions where you can gradually build up speed over months or years, but even advanced ion propulsion concepts struggle to reach the velocities needed for reasonable interstellar travel times. Nuclear propulsion offers more promise. Nuclear thermal rockets heat propellant using a nuclear reactor, achieving exhaust velocities much higher than chemical rockets. Nuclear pulse propulsion, like Project Orion conceived in the 1950s, involves detonating nuclear bombs behind your spacecraft and riding the shockwave. It sounds insane, and it kind of is, but the physics actually works. Calculations suggested an Orion-style ship could potentially reach 5 to 10% light speed. Then there's fusion propulsion. If we could master controlled nuclear fusion, the same process that powers the sun, we could theoretically achieve even higher speeds with less fuel mass. Concepts like the Daedalus probe, designed by the British Interplanetary Society in the 1970s, proposed a two-stage fusion rocket that could reach 12% light speed, making the journey to Alpha Centauri in about 40 years. But here's the reality check. We still haven't achieved sustained energy-positive fusion here on Earth, despite decades of research. The National Ignition Facility achieved fusion ignition in December 2022, producing more energy from fusion than the lasers put into the fuel pellet, but the overall system still consumed far more energy than it produced. Scaling that to a spacecraft engine that could run for decades is a challenge that might take another century to solve, if we solve it at all. And even if we do, even if we build a fusion-powered ship that can reach 10% light speed, we're still talking about 43 years in transit. 43 years of radiation exposure. 43 years of cosmic dust impacts. 43 years where everything has to work perfectly because there's no rescue mission coming. Let's talk about another radiation source you'd encounter. Your own propulsion system. If you're using nuclear thermal or nuclear pulse propulsion, you're essentially strapping yourself to a controlled nuclear reaction. The reactor or bomb debris produces intense radiation. You need heavy shielding between the engine and the crew compartment, which again adds mass. Some designs put the crew habitat at the far end of a long boom or tether, using distance as shielding. The farther you are from the radiation source, the weaker it gets, following the inverse square law. Double your distance, and radiation intensity drops to 1/4, but a long tether or boom creates its own engineering challenges. It needs to withstand acceleration forces, resist vibration, and remain structurally sound for decades. Any failure could leave your habitat swinging uncontrollably, or, worse, detaching entirely. Fusion propulsion is somewhat cleaner, producing less radioactive waste than fission, but it still generates neutron radiation that requires shielding. Antimatter propulsion, sometimes proposed as the ultimate rocket fuel, because matter-antimatter annihilation converts mass to energy with 100% efficiency, would produce gamma rays requiring extremely heavy shielding. There's another radiation concern that might surprise you: Bremsstrahlung radiation. Remember how we talked about interstellar medium particles slamming into your hull at relativistic speeds? When those high-energy particles hit your shielding and slow down, they emit X-rays through a process called Bremsstrahlung, which is German for braking radiation. Essentially, whenever you decelerate a charged particle, it releases photons. At relativistic speeds, the Bremsstrahlung X-rays can be energetic enough to penetrate into the crew compartment. A 2022 study published in the Astrophysical Journal by researchers at the University of California, Santa Barbara, including physicist Philip Lubin, calculated the radiation effects on relativistic spacecraft. They found that for a probe traveling at even 10 to 20% light speed, Bremsstrahlung radiation from interstellar medium collisions would be a significant hazard. The faster you go, the worse it gets. The radiation dose increases with velocity, creating yet another constraint on how fast you can safely travel. So radiation is trying to kill you from the outside, from your engines, and even from your own shielding interacting with space. What else could possibly go wrong? Well, let's talk about what happens if a solar particle event occurs while you're en route. Solar flares and coronal mass ejections are unpredictable. The Sun goes through an 11-year activity cycle, alternating between solar maximum, when flares and eruptions are common, and solar minimum, when they're less frequent but still possible. Even during solar minimum, the Sun can unleash massive particle storms with little warning. The Carrington event of 1859 was the most powerful solar storm in recorded history. It produced auroras visible as far south as the Caribbean and caused telegraph systems worldwide to fail, with some operators reporting shocks and sparking equipment. If a Carrington-scale event happened today, it could cripple satellites, damage power grids, and expose airline crews on polar routes to dangerous radiation levels in space without Earth's magnetosphere to protect you. A Carrington-class solar storm would be catastrophic. Within minutes to hours of a major solar flare, high-energy protons and heavier particles would begin arriving at your spacecraft. Flux rates could increase by factors of thousands or even millions compared to background levels. If you're caught outside the spacecraft during a spacewalk or in a lightly shielded section, you could receive a lethal dose in hours or even minutes. Your only defense is to have a designated storm shelter, a heavily shielded compartment where the crew can retreat during solar particle events. This shelter needs enough supplies to sustain everyone for days while the storm passes. The Orion spacecraft, being developed for NASA's Artemis missions, includes storm shelter provisions, using supplies and equipment arranged to provide additional shielding mass around a small area where astronauts can wait out solar storms. But here's the problem for an interstellar mission. Solar particle events can last for days, and they can come in clusters. During solar maximum, you might face multiple events per month. Over a 43-year journey, you'd almost certainly encounter dozens, possibly hundreds of solar storms. Each time the crew has to drop everything, squeeze into the shelter, and wait. It's like being on a ship in a perpetual hurricane zone, periodically diving below deck to ride out the worst tempests, and that's just our Sun. What about Alpha Centauri? Alpha Centauri A is slightly larger and more luminous than our Sun, while Alpha Centauri B is somewhat smaller and dimmer. Both are middle-aged stars similar to our Sun, which means they likely have their own activity cycles, flares, and particle emissions. As you approach the Alpha Centauri system, you'd be entering the activity zone of not one but two Sun-like stars. If they're both in active phases when you arrive, you could be dodging solar storms from multiple directions. Proxima Centauri, the red dwarf, is actually more worrying. Red dwarfs are known for violent flare activity. Observations by NASA's Chandra X-ray Observatory and other telescopes have shown that Proxima regularly unleashes flares thousands of times more powerful than the largest solar flares from our Sun. In March 2017, astronomers observed Proxima brightening by a factor of almost 70 in just a few seconds, releasing a blast of X-rays and ultraviolet radiation that would have bathed any nearby planets in sterilizing energy. If Proxima Centauri has planets in its habitable zone where liquid water could exist, those worlds are likely getting fried on a regular basis. For a spacecraft approaching the system, Proxima's flares would be another radiation hazard to monitor and avoid. Speaking of planets, let's consider the end goal. Why go to Alpha Centauri in the first place? In 2016, astronomers announced the discovery of Proxima Centauri b, an exoplanet orbiting Proxima in the star's habitable zone. With a minimum mass about 1.17 times Earth's mass, Proxima b could potentially be a rocky world where liquid water exists on the surface. It's the closest known exoplanet to Earth. Sitting just over 4 light-years away, the discovery sparked excitement and speculation. Could Proxima b harbor life? Could it be a future home for humanity? But subsequent observations paint a more complicated picture. Proxima b orbits extremely close to its star, completing one orbit every 11.2 days. It's likely tidally locked, meaning one side perpetually faces the star, while the other is in eternal darkness, just like the Moon always shows the same face to Earth. Tidal locking creates extreme temperature gradients unless the planet has a thick atmosphere to redistribute heat. And then there's the radiation. Proxima's frequent and violent flares bombard Proxima b with X-rays and particle radiation far more intense than anything Earth experiences. Unless the planet has an extremely strong magnetic field and thick atmosphere to shield its surface, it's probably a radiation-scorched wasteland, not a paradise waiting to be colonized. There might be other planets in the Alpha Centauri system we haven't discovered yet. Alpha Centauri A and B could have terrestrial worlds in their habitable zones that we simply can't detect with current technology because they're too small and too close to their bright parent stars. Finding out for sure would require sending probes to the system to conduct close-up observations. That's part of the motivation behind projects like Breakthrough Starshot, which proposes sending thousands of tiny, lightweight probes accelerated by powerful Earth-based lasers to 20% light speed. At that velocity, they'd reach Alpha Centauri in about 20 years. Each probe would carry cameras and instruments to study the system during a high-speed flyby, beaming data back to Earth. But those are robotic probes, not crewed missions. A flyby at 20% light speed wouldn't work for humans because you'd zip through the system in a matter of hours with no way to stop. If you want to send people, you need to slow down when you get there, which means you need even more energy and fuel for deceleration. The energy requirements become staggering. Kinetic energy, the energy of motion, is calculated using the formula 1/2 times mass times velocity squared. Let's say you're sending a relatively modest spacecraft with a mass of 1,000 metric tons, which is about the mass of the International Space Station. That's pretty minimal for an interstellar ship that needs to support a crew for decades, but we'll use it as a baseline. To accelerate that 1,000-ton spacecraft to 10% the speed of light, which is 30,000 kilometers per second, you need to give it kinetic energy. Plugging the numbers into the formula, you get approximately 4.5 times 10 to the 20th power joules. That's 450 million trillion joules. To put that in perspective, the entire world's energy consumption in 2023 was roughly 600 exajoules, which is 6 times 10 to the 20th power joules. So accelerating a single 1,000-ton spacecraft to 10% light speed requires about 3/4 of all the energy humanity produced and consumed in an entire year. And remember, you also need to decelerate when you arrive, which requires the same amount of energy again. So now you're talking about 1.5 times the world's annual energy production just to send one ship to Alpha Centauri. This is why interstellar travel is so monumentally difficult. The energy scales involved dwarf anything we currently do. Even if we master fusion power and can generate enormous amounts of energy, storing and using that energy efficiently in a propulsion system remains an unsolved engineering challenge. Some concepts try to work around this by not carrying all your fuel. Laser sail propulsion, for example, uses enormous ground-based or space-based lasers to push ultra-lightweight sails. The energy source stays home so the spacecraft can be much lighter. Breakthrough Starshot envisions tiny probes massing just a few grams, accelerated by a phased array laser system with gigawatts to terawatts of power. But laser sails have their own problems. First, they can only accelerate, not decelerate, unless you have a laser system waiting at your destination, which you obviously don't for a first mission. Some designs propose splitting the sail, using part of it to reflect laser light forward to slow down the remaining probe, but the physics gets extremely tricky. Second, keeping a laser focused on a tiny sail across trillions of kilometers is incredibly challenging. Even a perfectly collimated laser beam spreads out over distance due to diffraction. By the time your sail is even a fraction of a light year away, the laser beam has spread to enormous size, and only a tiny fraction of its energy still hits the sail. You'd need adaptive optics and incredibly precise targeting to keep the beam focused. Third, laser sails work best for tiny, lightweight probes. Scaling up to human-carrying spacecraft, massing hundreds or thousands of tons, requires sails hundreds of kilometers across and laser systems with power outputs that would make our current electrical grids look like flashlights. We're talking about engineering projects on scales humanity has never attempted. Magnetic sails offer another alternative. These use magnetic fields to interact with the interstellar medium's charged particles and magnetic fields, essentially sailing on the solar wind and interstellar plasma currents. They could potentially provide both acceleration when leaving the solar system and deceleration when approaching Alpha Centauri by changing the magnetic field configuration. But magnetic sails require extremely powerful magnetic fields generated by superconducting coils carrying enormous currents. They work best at moderate speeds, their effectiveness drops at very high velocities, and they rely on the interstellar medium being dense enough to push against, which isn't always the case. Space isn't uniformly filled. There are denser molecular clouds and thinner voids, and you can't always choose your path. Ramjet concepts, first proposed by physicist Robert Bussard in 1960. Imagine scooping up interstellar hydrogen with huge magnetic funnels and fusing it for propulsion. You'd be gathering fuel as you go, eliminating the need to carry it all from the start. The Bussard ramjet is an elegant idea that's inspired countless science fiction stories. Unfortunately, the physics doesn't quite work out. The interstellar medium is so thin that you'd need a scoop hundreds or thousands of kilometers wide to gather enough hydrogen for fusion. Creating and maintaining such an enormous magnetic field requires massive amounts of power. Worse, calculations show that the drag from scooping up all that material might actually slow you down more than the fusion thrust pushes you forward, at least until you're already moving at a significant fraction of light speed. You'd need another propulsion system to get you up to ramjet operating speed first. Every propulsion concept we can imagine with current physics has serious drawbacks. Some require technology we don't have and might not develop for centuries. Others require infrastructure investments on solar system-wide scales. Still others work in theory but would cost more resources than currently exist on Earth. This is the sobering reality of interstellar travel. It's not impossible according to the laws of physics, which is important. Physics doesn't forbid it, but engineering it with any technology we can foresee is almost incomprehensibly difficult. And we haven't even talked about what happens when you slow down. Let's say you've somehow solved the propulsion problem. You've accelerated to 10% light speed using fusion rockets, antimatter engines, laser sails, or some combination we haven't thought of yet. You've survived 4 decades of cosmic radiation, solar storms, and dust impacts. Alpha Centauri's stars grow brighter ahead, transitioning from points of light to actual disks. You're almost there. Now you need to stop. If you don't decelerate, you'll shoot through the Alpha Centauri system in a matter of hours. Barely enough time to snap a few photos before you vanish back into the interstellar void, never to return. Deceleration requires thrust in the opposite direction, which means you need either fuel reserves you've carried the entire way, a deceleration system like a magnetic sail that can interact with Alpha Centauri's stellar wind, or some other mechanism we haven't invented yet. If you're carrying fuel for deceleration, you had to accelerate that fuel mass too, which means your initial energy requirements were even higher than the already staggering numbers we calculated. The rocket equation bites you twice, once on the way up and again on the way down. Some mission profiles propose using gravitational assists from bodies in the Alpha Centauri system, swinging around stars or planets to shed velocity. But gravitational assists only work if there are conveniently placed massive objects in the right positions, and you need to approach them at the right angles and speeds. You can't count on the system's architecture being cooperative. Another deceleration concept involves deploying a huge magnetic field or plasma's break that interacts with the destination star's stellar wind and magnetic environment. As charged particles from Alpha Centauri's solar wind hit your magnetic field, they transfer momentum, gradually slowing you down. This could work, but it requires getting close enough to the stars for their stellar winds to be dense enough, and it would take years of gradual braking. During that time, you're exposed to increasingly intense radiation as you approach the stars. Let's imagine you've somehow managed to decelerate and enter orbit around Proxima Centauri b, or another planet in the system. You're exhausted. Your equipment has been degraded by decades of radiation exposure, and you're ready to complete your mission, but you're not out of danger yet. In fact, you might just be entering the most hazardous phase. If Proxima b has an atmosphere and you want to land, you're attempting atmospheric entry at a planet you've never visited before. You don't know the atmospheric composition with certainty, its density profile, wind patterns, or weather systems. Your heat shield needs to be designed for conditions you can only estimate. If the atmosphere is thicker than expected, you could burn up. If it's thinner, you might not slow down enough and crash. Earth's atmosphere is deadly enough to enter, and we know it intimately. Every spacecraft returning from orbit or the moon has to survive the screaming plunge through superheated plasma with hull temperatures exceeding 1500 degrees Celsius. The space shuttle used specially designed heat-resistant tiles. Apollo capsules used ablative heat shields that charred and vaporized, carrying heat away. Any failure in the heat shield means instant death. Now imagine doing that at an alien world where your atmospheric models might be wrong, where you have no weather satellites to warn you of storms, where the magnetic field configuration, if there is one, is unknown. You get one chance to get it right, and if you do land successfully, you're now on the surface of an alien world that has been bathed in radiation from Proxima's flares for billions of years. The soil might be laced with peroxides and oxidizing compounds similar to those found on Mars, making it chemically reactive and potentially toxic. The atmosphere, if breathable at all, could contain trace gases or compounds hazardous to human health. You'd need habitats that protect you not just from the outside environment, but from the ongoing radiation bombardment. Living on Proxima b would mean spending most of your time underground or in heavily shielded structures. Surface exploration would require suits that provide radiation protection in addition to life support. And here's a thought that should chill you. There's no going home. Even if your spacecraft is somehow still functional after decades in space and the stress of deceleration, you don't have the fuel or energy to accelerate back to 10% light speed for the return journey. You'd need to refuel using local resources, assuming they exist and you can extract them. Producing rocket fuel on an alien world with unknown geology and chemistry is a colossal challenge. Realistically, anyone who makes the journey to Alpha Centauri is going one way. They're committing themselves and possibly generations of descendants to living in that distant star system forever. Earth will be a mythical homeworld their grandchildren hear stories about but never see. This is why when people talk seriously about interstellar colonization, they often discuss generation ships, enormous vessels where multiple generations live and die during the journey. Your great-great-grandchildren might be the ones who arrive at the destination, not you, but generation ships introduce a whole new category of dangers, psychological and sociological rather than physical. Can a closed society maintain cohesion and purpose across centuries? What happens when the third generation questions why they should continue a journey they never chose? How do you prevent genetic bottlenecks in a small population isolated from the rest of humanity? These questions go beyond astrophysics into anthropology, psychology, and ethics, and the answers are uncertain at best. Humans have never attempted anything remotely similar. Our longest duration closed ecological experiment, Biosphere 2 in Arizona during the 1990s, barely lasted 2 years before serious problems emerged, and that was with the entire Earth just outside. Let's get back to the immediate physical dangers. We've covered radiation, propulsion challenges, and deceleration. What else could kill you? Micrometeorites and space debris. We mentioned dust impacts earlier, but let's go deeper. Space isn't perfectly empty. In addition to individual atoms and molecules, the interstellar medium contains tiny solid particles, grains of dust, typically a few micrometers to millimeters in size. These grains are made of various materials, silicates, carbon compounds, ices. They're the building blocks of future planets, condensed from the ashes of dead stars and scattered through the galaxy. At rest, they're harmless, but at 10% light speed, a dust grain becomes a devastating projectile. Kinetic energy increases with the square of velocity. Double your speed and your kinetic energy quadruples. At 30,000 kilometers per second, even a particle with the mass of a grain of sand carries enormous destructive energy. A micrometeorite just 1/10 of a millimeter across, roughly the width of a human hair, hitting your spacecraft at that speed would release energy equivalent to several kilograms of TNT, exploding on impact. The International Space Station, orbiting Earth at about 7.66 kilometers per second, already faces micrometeorite hazards. NASA tracks thousands of pieces of orbital debris and occasionally maneuvers the station to avoid potential collisions. The station's modules have Whipple shields, multi-layered bumpers designed to vaporize incoming particles before they reach the pressure hull. Even with this protection, windows have been chipped and solar panels damaged by tiny impacts. Now multiply those orbital velocities by 4,000. At interstellar speeds, the damage potential is catastrophic. Your spacecraft needs layered shielding designed specifically to handle hypervelocity impacts. The first layer, positioned meters ahead of the main hull, is meant to vaporize incoming particles into plasma. Subsequent layers absorb and dissipate that plasma's energy before it can penetrate to the crew compartment. This spacing is crucial. If the layers are too close together, the plasma cloud doesn't have room to expand and cool before hitting the next barrier. But here's the engineering nightmare. You can't shield everything equally. Solar panels, radiators, sensors, communications antennas, and other external equipment must be exposed to function. These vulnerable components face the same impact hazard as the hull. A single dust grain puncturing a coolant line, shattering a sensor array, or punching through a power cable could cascade into system failures. Redundancy becomes essential. You need backup systems for backups, multiple independent paths for critical functions, and the ability to isolate damaged sections. Your spacecraft is essentially a complex network where every node is under constant threat. Maintaining that network across decades requires reliability engineering far beyond anything we've achieved. Consider the Voyager probes. Launched in 1977, they're the longest operating spacecraft in history, still functioning after nearly 50 years, but they're gradually dying. Power from their plutonium radioisotope thermoelectric generators declines by about 4 watts per year. Instruments have been shut down one by one to conserve electricity. Communications require NASA's largest antennas to hear their faint signals across billions of kilometers. Voyagers are relatively simple machines by modern standards, and they're flying through relatively empty space in the outer solar system and beyond. They're not supporting human life, recycling air and water, growing food, or maintaining comfortable temperatures. And they're definitely not traveling at 10% light speed through the denser interstellar medium. A crude interstellar ship would be orders of magnitude more complex, with thousands of systems that all need to work continuously for decades. The reliability requirements are almost impossible to meet. Even if each individual component has a 99.9% chance of working for 40 years, when you have tens of thousands of components, failures become inevitable. You need manufacturing capability on board, three-dimensional printers that can fabricate replacement parts from raw materials, machine shops with lathes, mills, and fabrication equipment, electronics repair facilities, trained crew members who can diagnose problems and improvise solutions with whatever materials are available. You're essentially sailing an isolated industrial facility through the void, cut off from any supply chain. If you want to explore more impossible questions like this, make sure to hit that subscribe button. Trust me, we're just getting started, and you need to protect that capability from radiation too. Electronics are particularly vulnerable to cosmic rays. A single heavy ion passing through a computer chip can flip bits in memory, causing data corruption. These single-event upsets happen regularly on satellites and the International Space Station. Most are harmless, caught and corrected by error-checking codes, but occasionally they cause serious malfunctions. In 1997, a cosmic ray hit a Motorola satellite, flipping a bit that caused the spacecraft's computer to reset and triggered a sequence of events that left it tumbling uncontrolled. It took weeks to recover. In 2008, a cosmic ray struck a computer aboard a Qantas airliner at cruising altitude, causing the autopilot to malfunction and pitch the nose down violently, injuring dozens of passengers. On an interstellar journey, you're exposed to cosmic ray flux far more intense than low Earth orbit experiences, and for far longer than any airplane flight. Your computers will be hit thousands of times. Radiation-hardened electronics help, but they're expensive, heavier, and still not perfect. You need extensive error correction, redundant processing, and constant monitoring to catch glitches before they cascade into disasters. Biological systems face similar challenges. We already discussed radiation's effects on human health, but let's talk about the spacecraft's life support ecosystem. Humans need oxygen to breathe, water to drink, and food to eat. On short missions, you can carry supplies. The Apollo lunar missions carried oxygen tanks, water, and freeze-dried food. The International Space Station is regularly resupplied by cargo spacecraft from Earth. An interstellar mission can't rely on resupply. Everything must be recycled in a closed-loop system. The ISS already does this to a degree. The Environmental Control and Life Support System recycles about 93% of water from urine, sweat, and humidity condensed from the air. Carbon dioxide exhaled by astronauts is scrubbed from the air and either vented overboard or split into oxygen and carbon, but the ISS still requires regular deliveries of food, spare parts, and make-up oxygen to replace losses. Over a 40-year interstellar voyage, you need true closure, recycling approaching 100% efficiency, because even small losses compound over time. Let's do the math. A human needs about 0.84 kilograms of oxygen per day. Over 40 years, that's roughly 12,000 kilograms per person. A crew of, say, 50 people would need 600,000 kilograms of oxygen if you're not recycling. That's 600 metric tons, more than half the mass of our hypothetical spacecraft. Water requirements are similar. Humans need about 2 liters of drinking water per day, plus more for hygiene and food preparation. Even with aggressive recycling, you need buffer reserves to handle equipment failures and losses. Food is the biggest challenge. Plants can theoretically recycle carbon dioxide into oxygen while producing edible biomass, creating a closed ecological loop. But growing enough food for dozens of people in the limited space and energy budget of a spacecraft is extraordinarily difficult. Biosphere 2, the 3.1-hectare sealed facility in Arizona we mentioned earlier, attempted to support 8 people in a closed ecological system. Despite having far more space and resources than any spacecraft could afford, the project struggled. Oxygen levels dropped unexpectedly because soil microbes consumed more oxygen than anticipated. Carbon dioxide spiked, food production fell short, and crew members lost significant weight. After 16 months, outside oxygen had to be pumped in. Scaling that down to a spacecraft where every cubic meter and every watt matters makes the challenge even harder. You'd likely rely on a hybrid approach. Highly efficient hydroponic or aeroponic crop growth for some food, supplemented by compact stored rations like spirulina algae cultivated in bioreactors. It works in theory. Making it work reliably for 40 years is another matter. And plants, like humans, are affected by radiation. Cosmic rays damage plant DNA, potentially reducing crop yields or causing mutations. You'd need to shield your agricultural sections, adding more mass to an already mass-constrained design. Then there's the psychological challenge of eating the same limited menu for decades. Variety in diet isn't just about enjoyment. It's important for nutrition and mental health. Monotonous food contributes to appetite loss, nutritional deficiencies, and depression. Astronauts on the ISS consistently rate food quality as one of their top concerns, and their missions last months, not decades. Let's talk about temperature control, because this is another way space tries to kill you that people often overlook. In space, you can't regulate temperature the way you do on Earth. On our planet, if something gets too hot, heat conducts into the surrounding air, which carries it away through convection. In the vacuum of space, there's no air. The only way to shed heat is through thermal radiation, emitting infrared photons that carry energy away. This matters because every system on your spacecraft produces heat. Your nuclear reactor or fusion engine generates enormous amounts. Electronics produce heat. Human bodies produce heat, about 100 watts per person continuously. Lights, computers, life support machinery all contribute to a heat load that must be radiated away, or your spacecraft will slowly cook. Heat rejection in space requires radiators, large surface areas that emit infrared radiation. The space shuttle had radiator panels. The ISS has enormous radiators that glow visibly in infrared images. For an interstellar ship with high power requirements, you'd need radiators covering thousands of square meters. But radiators facing forward in the direction of travel would be sandblasted by interstellar dust impacts. You'd need to orient them perpendicular to your velocity vector, which constrains your spacecraft's shape and configuration. And radiators, being large and thin, are vulnerable to micrometeorite damage. A puncture in a fluid-filled radiator loop would leak coolant, potentially crippling your thermal control system. Backup cooling systems add mass and complexity. You could use redundant loops, isolating damaged sections. You could carry reserve coolant to replace losses. But everything has limits, enough damage, and you can't reject heat fast enough. Temperatures rise, electronics fail. Habitable areas become ovens. The flip side is equally dangerous. If your power systems fail, you lose heating. Without active heating, radiative cooling to the near absolute zero background temperature of space would eventually freeze everything solid. You'd have some time. Thermal inertia would keep things warm for a while, but without a functioning power source, you're on a countdown to freezing death. This is why redundancy in power generation is absolutely critical. You can't rely on a single reactor or engine. You need multiple independent power sources, ideally different types, so a single failure mode doesn't take them all down simultaneously. Maybe a primary fusion reactor backed up by fission reactors, backed up again by radioisotope thermoelectric generators, with solar panels as an emergency option if you're close enough to a star. Each backup system adds mass, cost, and complexity, but without them, a single point failure ends the mission and everyone aboard. Speaking of power, let's consider the sheer energy budget required. We've talked about propulsion energy, but what about the continuous power needs for life support, computers, communications, and all other systems? The ISS uses about 75 to 90 kilowatts of electrical power generated by its massive solar arrays. Those arrays cover about 2,500 square meters, larger than a basketball court. For an interstellar ship, solar power becomes less useful once you're far from the sun. Solar intensity drops with the square of distance. At Jupiter's orbit, about 5 times Earth's distance from the sun, solar panels receive only about 4% as much light. Beyond Neptune, solar power is nearly useless. You need nuclear power. Fission reactors are proven technology. We've used them on Earth for decades and on a few space missions. The Soviet Roressat satellites used small reactors. NASA's Killer Power project is developing compact reactors for Mars bases and deep space missions. Scaling up to hundreds of kilowatts or even megawatts for an interstellar ship is an engineering challenge, but it's within our capabilities. Fusion reactors, if we can make them work, would be more compact and efficient for a given power output. But again, we're betting on technology we haven't fully developed yet. Whatever power source you use, it needs to operate continuously for 40+ years without major maintenance shutdowns. Terrestrial power plants undergo regular maintenance, replacing worn components, refueling, and upgrading systems. Your interstellar reactor has to keep running with only the maintenance you can perform using onboard resources. Fuel is another consideration. If you're using fission, you need uranium or plutonium. The mass of fissionable material required depends on your power needs and the reactor's efficiency, but you're talking about tons of radioactive fuel that must be shielded and handled carefully. If you're using fusion, you need deuterium and tritium, or perhaps helium-3, depending on your fusion reaction. Some of these fuels are easier to obtain than others. Helium-3 is extremely rare on Earth but might be harvested from the lunar surface or gas giant atmospheres, adding another layer of infrastructure needed before you even launch. Let's talk about navigation, because finding your way across interstellar distances introduces challenges you don't face in the solar system. Within our solar system, we navigate using radio signals and precise tracking of planetary positions. NASA's Deep Space Network, a collection of giant radio antennas in California, Spain, and Australia, communicates with distant spacecraft, measuring their positions using Doppler shifts and signal timing. We know where planets are with extraordinary precision because we've observed them for centuries and modeled their orbits using Newtonian mechanics and general relativity. In interstellar space, those familiar landmarks vanish. Earth becomes a pale blue dot, then disappears entirely. The sun becomes just another star among thousands. You're navigating through a three-dimensional void with no obvious reference points. Pulsars offer one solution. These rapidly rotating neutron stars emit beams of radio waves that sweep across space like cosmic lighthouses. Their rotation rates are incredibly stable, some keeping time more accurately than atomic clocks. By measuring the arrival times of pulses from multiple known pulsars, you can triangulate your position in the galaxy. This concept, called X-ray pulsar navigation, has been tested on Earth-orbiting satellites. China's pulsar navigation experiment aboard the Tiangong-2 space station demonstrated the technique in 2016 and 2017. For an interstellar mission, pulsar navigation becomes not just useful but essential. However, you need updated star catalogues. The positions of stars change over time due to their own motions through the galaxy, a phenomenon called proper motion. For nearby stars like those in the Alpha Centauri system, proper motion is measurable even over decades. The stars you see when you arrive won't be in exactly the same positions relative to background stars as they were when you left Earth 40 years earlier. Your navigation computer needs to account for this, constantly updating your position based on pulsar timing, optical observations of stars ahead and behind, and Doppler measurements of your velocity relative to known objects. Any error compounds over time. A tiny navigation mistake early in the journey could put you thousands of kilometers off course by the time you reach Alpha Centauri, potentially causing you to miss the system entirely or arrive at the wrong angle for gravitational braking or planet intercept. And there's another problem: relativity. At 10% light speed, relativistic effects start to become noticeable. Time aboard your spacecraft passes slightly slower than time back on Earth, an effect called time dilation. The difference is small at this speed, but it exists. Your clocks, both mechanical and biological, tick a tiny bit slower than clocks on Earth. The Lorentz factor, which describes this time dilation, is 1 divided by the square root of 1 minus velocity squared divided by the speed of light squared. At 10% light speed, the Lorentz factor is approximately 1.005. That means for every 100 days that pass on Earth, only about 99.5 days pass aboard your ship. Over a 43-year journey, that's a difference of several months. It sounds small, but it matters for navigation and communication timing. When you're calculating trajectories and predicting where celestial objects will be, you need to account for whose clock you're using. At higher speeds, relativistic effects become more dramatic. If you could somehow reach 50% light speed, the Lorentz factor increases to about 1.15, meaning time aboard your ship would pass about 13% slower. At 90% light speed, the Lorentz factor jumps to 2.3. Time aboard runs less than half as fast as time on Earth. Science fiction often depicts near light speed travel, where crew members age only a few years, while decades or centuries pass on Earth. The physics actually supports this, but reaching those speeds requires energy we can barely comprehend. To accelerate our 1,000-ton spacecraft to 90% light speed would require kinetic energy of about 3.6 times 10 to the 21st joules, roughly 6 times the total annual energy consumption of all human civilization. And at those speeds, the interstellar medium becomes a serious radiation hazard in a new way. Even individual hydrogen atoms hitting your hull at 90% light speed carry enough energy to create particle cascades when they impact. The forward-facing surfaces of your ship would be continuously bombarded by what effectively becomes a beam of high-energy protons. You'd need enormously thick shielding just to survive the journey. Some designs propose magnetic deflector shields, generating powerful magnetic fields ahead of the spacecraft to push charged particles aside before they hit the hull. This sounds like science fiction, and it mostly is with current technology, but the physics is sound. A sufficiently strong magnetic field can deflect incoming protons and other charged particles. The problem is generating and maintaining such a field requires enormous amounts of power, superconducting magnets that must be kept at temperatures near absolute zero. and massive structural support to resist the forces. We've built powerful magnets for particle accelerators like the Large Hadron Collider, which uses superconducting magnets generating fields of about 8.3 Tesla. Scaling that up to deflect particles across a spacecraft-sized area traveling at relativistic speeds is theoretically possible but practically daunting, and magnetic fields only deflect charged particles. They do nothing against neutral particles like neutrons, or photons like gamma rays and X-rays. You still need physical shielding for those. Let's discuss communications, because staying in touch with Earth presents its own lethal challenges, or at least challenges that become lethal if you lose contact at a critical moment. Radio signals travel at light speed. When you're 4.37 light-years away at Alpha Centauri, any message you send takes 4.37 years to reach Earth. A reply takes another 4.37 years to get back to you. Round-trip communication takes 8.74 years. That means if you encounter a problem and radio Earth for help, the response arrives nearly 9 years later. Whatever crisis you're facing, you're entirely on your own for solving it. Mission Control can't help in real time. They can't troubleshoot failures, offer advice during emergencies, or provide psychological support when it matters. This communication lag fundamentally changes the relationship between spacecraft and ground support. On Apollo lunar missions, communication delays were barely a second. Controllers on Earth could offer real-time guidance. On Mars missions, the delay ranges from about 3 to 22 minutes depending on planetary positions, long enough that rovers need significant autonomous capability, but short enough that daily planning cycles work. At interstellar distances, you're operating a completely independent outpost. The crew makes all decisions. Mistakes are theirs to fix or suffer. There's profound psychological weight to that isolation, and maintaining communication across light years is technically challenging. Radio signals weaken with distance following the inverse square law. Double the distance and signal strength drops to 1/4. At interstellar ranges, even powerful transmitters produce signals that are incredibly faint by the time they reach their destination. The Voyager 1 probe, now about 23 billion kilometers from Earth, roughly 154 times Earth's distance from the Sun, transmits at 23 watts using a 3.7-meter dish antenna. By the time those signals reach Earth, they've spread over an enormous area, and the power received by NASA's 70-meter Deep Space Network antennas is about 1 × 10⁻18 watts, a billionth of a watt. That's comparable to the power a cell phone would receive from a transmitter on the Moon. At Alpha Centauri's distance, about 280,000 times farther than Voyager 1 is now, signal strength would be roughly 30 billion times weaker if you're using similar equipment. You'd need either vastly more powerful transmitters, larger antennas, or both. Laser communications offer a potential solution. Lasers can be focused into extremely tight beams, concentrating power in a narrow cone rather than spreading it in all directions like radio waves. NASA has successfully tested laser communications on missions like the Lunar Laser Communication Demonstration in 2013, achieving data rates hundreds of times faster than radio with less power. For interstellar distances, high-powered lasers could potentially maintain data links, but pointing accuracy becomes critical. At 4 light-years, even a tiny pointing error causes your beam to miss Earth entirely. You need incredibly precise star trackers, gyroscopes, and pointing mechanisms that can hold position within fractions of an arcsecond, despite your spacecraft's vibrations, course corrections, and structural flexing. And lasers can be blocked by dust and debris. If a dust cloud drifts between you and Earth, communications are cut off until you emerge. Radio waves can sometimes scatter around obstacles, but laser beams are line of sight only. There's another communication concern: data storage. As your mission progresses, you accumulate scientific data about the interstellar medium, measurements of cosmic rays, observations of Alpha Centauri growing closer. If you lose communication ability or power fails, that data must be preserved somehow for eventual transmission or physical return. Radiation damages data storage media. Hard drives can suffer bit flips. Solid-state memory degrades over time, especially under radiation exposure. Optical media like specialized archival disks might last longer but have limited capacity. You need redundant storage across multiple physically separated systems with constant error checking and correction to ensure data integrity over decades. Consider the cultural and scientific knowledge you'd want to bring with you. A comprehensive library of human knowledge, technical manuals, medical references, entertainment, music, art, history. All the accumulated wisdom of civilization compressed into digital formats and protected against loss. The Long Now Foundation's Rosetta project created a micro-etched nickel disc containing translations of over 1,500 languages designed to last thousands of years. For an interstellar mission, you'd need something similar but vastly larger in scope and protected against radiation damage. You're not just carrying data for a few decades, you're potentially founding a new branch of human civilization that might never have contact with Earth again. Everything they'll need to know must come with them. Let's talk about something we haven't addressed yet. What happens if someone dies during the journey? On Earth, when a person dies, we have established cultural and practical procedures: burial, cremation, or other rituals depending on beliefs and traditions. Bodies are handled in ways that prevent disease transmission and honor the deceased. In space, you can't bury anyone. There's no ground. You can't simply open an airlock and jettison the body into space, although that's what science fiction sometimes depicts. Well, technically you could, but it raises ethical, cultural, and even practical questions. From a practical standpoint, a human body contains water, organic molecules, and elements that might be valuable in a closed-loop life support system. In the harsh calculus of resource conservation on a decades-long voyage, those materials represent resources that could be recycled. The human body contains about 42 liters of water, roughly 11 gallons. That water could be reclaimed and purified. The organic matter could be broken down and potentially used to fertilize hydroponic crops. This sounds horrifying when stated bluntly, and it is. We're talking about treating human remains as recyclable resources. But in the extreme environment of an isolated spacecraft where every molecule matters for survival, these decisions might become necessary. Cultures would need to evolve new rituals and beliefs that accommodate these realities. Alternatively, you could preserve bodies in cold storage, taking advantage of space's natural deep freeze environment. A compartment exposed to vacuum and shadow would maintain temperatures near absolute zero, effectively freeze-drying and preserving remains indefinitely, perhaps for eventual burial at the destination, or return to Earth if that ever becomes possible, or simply as a way to honor the deceased without consuming resources. But cold storage requires space, a commodity that's expensive on a spacecraft. Every cubic meter dedicated to storing bodies is space not available for equipment, supplies, or living quarters. How many deaths do you plan for? What's the acceptable allocation of space for remains? These aren't purely hypothetical concerns. Actuarial tables can estimate mortality rates for a population of a given age and health over time. Even if you select the healthiest crew members and provide excellent medical care, some deaths are statistically inevitable over 40 years. Accidents happen. People develop cancers, perhaps radiation-induced, cardiovascular disease, strokes, infections that don't respond to available antibiotics. Medical emergencies that would be survivable on Earth might be fatal without access to specialized equipment or surgical facilities. Your spacecraft needs a medical facility capable of handling everything from routine checkups to emergency surgery. You need diagnostic equipment, X-ray or better yet MRI machines, though MRI scanners are heavy and power-hungry, laboratory equipment for analyzing blood, culturing bacteria to identify infections, preparing and examining tissue samples, a pharmacy with a comprehensive selection of medications, enough to last decades, accounting for expiration dates. Some medications remain potent for years, others degrade. You need either supplies that last or the ability to manufacture pharmaceuticals on board. Surgical capability means an operating room with sterilization equipment, surgical instruments, anesthesia machines, and monitoring devices. You need surgeons trained in multiple specialties because you can't bring specialists for every possible medical situation. Imagine a general practitioner who must also be competent in orthopedic surgery, neurosurgery, obstetrics, dentistry, and everything else that might arise. Medical emergencies happen at inconvenient times. What if your only surgeon is incapacitated when someone else needs emergency surgery? Redundancy in medical training becomes essential. Multiple crew members need surgical skills. But training someone to surgical competency takes years. Medical school and residency on Earth span roughly a decade. You need crew members who've already completed that training before launch, and you need enough of them. Your crew size starts to grow. Pilots, navigators, engineers specializing in propulsion, life support, electrical systems, computers, structural maintenance, scientists to conduct research and study Alpha Centauri, agricultural specialists to manage food production, medical personnel, psychologists to monitor and support mental health, teachers if you're on a multi-generational ship and children are born during the voyage. Each additional crew member requires life support resources, living space, food, water, oxygen. They add mass. They increase the likelihood of interpersonal conflicts. But too small a crew means you lack essential skills when problems arise. There's a concept in systems engineering called the bus factor. How many team members can be hit by a bus before a project fails? For critical functions on an interstellar ship, you want a bus factor of at least 3, maybe more. 3 people who can perform emergency surgery, 3 who can repair the reactor, 3 who can maintain the navigation systems. Redundancy saves lives. Genetic diversity matters too if you're establishing a permanent colony. Small populations risk inbreeding, genetic drift, and the accumulation of harmful mutations. Population geneticists suggest a minimum of several hundred individuals to maintain healthy genetic diversity across multiple generations, though the exact number depends on various factors. But we're already talking about scaling the mission far beyond a small spacecraft. Hundreds of people require life support infrastructure on an enormous scale. We're now discussing generation ships kilometers long, rotating to provide artificial gravity, with ecosystems complex enough to support populations for centuries. These designs have been proposed. The Stanford Torus, conceived at a NASA summer study in 1975, envisioned a rotating space station 1.8 kilometers in diameter, housing 10,000 people. The O'Neill cylinder, proposed by physicist Gerard K. O'Neill, consists of 2 counter-rotating cylinders several kilometers in diameter and 32 kilometers long, each capable of housing millions in Earth-like conditions with artificial gravity from rotation. These are staggering engineering projects. The mass of such structures, built from steel, aluminum, composites, and shielding materials, would measure millions of tons. Accelerating an O'Neill cylinder to even a fraction of light speed requires energy expenditures that make our earlier calculations look trivial. Perhaps you don't accelerate the whole structure. Maybe you send the cylinder slowly, coasting through space at speeds of just a few % of light speed, extending the journey to a century or more, but requiring less energy. Generations live and die aboard. The journey itself becomes home, but this introduces the psychological and sociological dangers we mentioned. Can a society remain stable and purposeful across multiple generations confined to a closed environment? Earth's sailing ships in the age of exploration sometimes spent months at sea, and mutinies, disease outbreaks, and psychological breakdowns occurred regularly. The longest Antarctic expeditions, where teams overwinter in isolated bases for months, report psychological stress, interpersonal conflicts, and mental health challenges despite modern communication with the outside world. And the knowledge that they'll eventually go home. Your generation ship crew doesn't have those comforts. There's no outside world to communicate with in real time. Earth's messages arrive years late, increasingly irrelevant to the ship's immediate reality. There's no going home. The mission is multi-generational, and after a few generations, the destination is abstract, a place great-grandparents dreamed of but no living person has seen. Why should the third or fourth generation continue the journey? They were born into a situation they didn't choose. Their entire universe is the interior of the ship. Earth and Alpha Centauri are both equally mythical, just stories told by elders. Some might argue for changing course, turning around, or even abandoning the mission in favor of remaining in interstellar space forever. You'd need social structures that maintain purpose and cohesion, perhaps a culture that venerates the mission as sacred duty, educational systems that emphasize the importance of reaching the destination, governance that balances authority with participation, preventing tyranny but maintaining order, entertainment and recreation to keep people engaged and hopeful, but enforcing this over generations when people inevitably develop divergent ideas is challenging. Do you suppress dissent to preserve mission cohesion, risking authoritarianism? Do you allow free expression and debate, risking the mission's dissolution? There are no easy answers. And what about reproduction? On a multi-generational ship, children will be born during the voyage. Do you regulate population to match life support capacity? Who decides who can have children and how many? These deeply personal decisions become matters of collective survival. Uncontrolled population growth could overwhelm life support systems. Too few births, and the population ages and dwindles. Genetic diversity requires a certain population size, but maintaining that population requires resources. It's a delicate balance. Earth has grappled with population ethics and never reached consensus. Different cultures, religions, and philosophies hold different views on reproductive rights and freedoms. Imposing population controls on an interstellar mission would create ethical dilemmas and potential resistance. Perhaps genetic engineering offers solutions. If you can select embryos or modify genetics to minimize hereditary diseases and maximize health, you reduce the genetic diversity needed. But genetic engineering introduces its own ethical questions, and mistakes could have consequences that echo through generations. And we still haven't solved the fundamental problem. Even if you successfully navigate all these social, psychological, and engineering challenges and reach Alpha Centauri, you're arriving at a destination you know very little about. Our best observations of Proxima Centauri b come from transit photometry, measuring the slight dimming of Proxima's light as the planet passes in front, and radial velocity measurements detecting the star's wobble caused by the planet's gravity. These methods tell us the planet's size, approximate mass, and orbital distance. We can make educated guesses about whether it might have an atmosphere and surface conditions, but we don't know for certain. We can't see surface features. We don't know if there's water, what the atmospheric composition is, whether there's life, or even if the planet is remotely habitable. we're basing a mission that costs unimaginable resources and commits people to decades or generations of travel on indirect observations and probabilistic models. What if you arrive and find Proxima b is a barren rock, tidally locked with one side perpetually scorched and the other frozen, with no atmosphere to speak of? Or an atmosphere so thick with carbon dioxide that the surface pressure would crush you, like being a kilometer underwater on Earth? What if the radiation environment is even worse than predicted, with Proxima's flares having stripped any atmosphere long ago and sterilized the surface? What if there's life, but it's biochemically incompatible or outright toxic to Earth organisms? Or worse, what if there are microbes that can infect humans, causing diseases we have no immunity to and no way to treat? The Outer Space Treaty of 1967 includes provisions for planetary protection, preventing contamination of celestial bodies with Earth life, and protecting Earth from potential extraterrestrial contamination. NASA and other space agencies follow strict protocols for sterilizing spacecraft that will land on Mars or other bodies where life might exist. For an interstellar mission, planetary protection becomes even more critical. You're potentially introducing Earth microbes to an entirely different biosphere or bringing alien organisms back to your spacecraft. Cross-contamination could devastate either ecosystem or both. Sterilization protocols would need to be extreme. Any landing craft or rovers that touch Proxima b's surface would need to be thoroughly sterilized beforehand. Samples returned to the spacecraft would need to be quarantined and analyzed extensively before exposure to the crew or life support systems. But here's the problem. Humans are walking colonies of microorganisms. Your body contains roughly 30 trillion human cells and about 39 trillion bacterial cells. Your gut microbiome, skin flora, and other symbiotic organisms are essential for your health. You can't sterilize a human being. If humans land on Proxima b, they inevitably bring Earth microbes with them. Spacesuits can be sterilized externally, but they're not perfect seals. Equipment, tools, and eventually habitats will leak organisms. If there's any way for Earth microbes to survive in Proxima b's environment, contamination is inevitable. This might not matter if Proxima b is sterile, but if there's native life, you've potentially introduced an invasive species on a planetary scale. Earth's history is full of examples where introducing foreign species devastated native ecosystems. Rabbits in Australia, kudzu in the American South, zebra mussels in the Great Lakes. Now imagine that on an alien world, and the reverse problem. If Proxima b has life, even microbial, you risk bringing it back to your spacecraft. Alien biochemistry might be incompatible with Earth-based life, rendering it harmless, or it might interact in unexpected ways. Viruses are highly specific to their hosts on Earth, but bacteria can sometimes exchange genetic material across species. The possibilities are unknown and potentially dangerous. You'd need quarantine facilities, airlocks with sterilization cycles, and protocols for handling samples. Laboratories equipped to study alien biochemistry safely, isolated from life support systems. Trained astrobiologists who can analyze specimens and assess risks. All of this adds more mass, more complexity, and more points of potential failure. Let's consider another scenario. What if Proxima b is habitable, or at least has resources you can use, but it's not quite Earth-like? Maybe the atmosphere is breathable but thin, requiring acclimatization or supplemental oxygen. Maybe gravity is different enough to cause health issues over time. Maybe day-night cycles, if they exist at all on a potentially tidally locked planet, don't match human circadian rhythms. Humans are adaptable, but we evolved for Earth-specific conditions. Gravity affects bone density, muscle mass, cardiovascular function, and even how fluids distribute in your body. We've seen these effects on astronauts in microgravity. Proxima b's gravity is estimated at around 1.07 times Earth's, slightly higher. That's probably tolerable, but we don't have experience with long-term habitation at that level. Atmospheric pressure and composition matter enormously. Earth's atmosphere is about 78% nitrogen, 21% oxygen, and trace amounts of other gases at an average pressure of 101.3 kilopascals at sea level. You can tolerate lower pressures if oxygen concentration is higher, as demonstrated by high-altitude mountaineers and low-pressure spacecraft environments, but there are limits. Too much oxygen is toxic. Prolonged exposure to pure oxygen at Earth normal pressure causes lung damage within days, a condition called oxygen toxicity. Too little and you suffer hypoxia, oxygen starvation that leads to unconsciousness and death within minutes. If Proxima B's atmosphere has significant amounts of gases toxic to humans, carbon monoxide, sulfur dioxide, methane, ammonia, you'd need to wear respirators or live in sealed habitats indefinitely. That's manageable but constraining. You haven't really colonized a planet if you're confined to artificial environments, no different from the spacecraft you arrived in. Temperature swings could be severe, especially if the planet is tidally locked. One hemisphere always faces the star, the other always faces away. The day side might be scorching, the night side frozen. Habitable zones might exist only in the twilight band between, where temperatures are moderate, but twilight zones on a tidally locked planet would experience constant twilight, never true day or night. Psychologically, that's challenging for humans adapted to day-night cycles, and then there's the possibility of weather. If Proxima b has an atmosphere and temperature differentials, it has weather patterns. Tidally locked planets might experience fierce winds as air constantly circulates from the hot day side to the cold night side and back. Storms could be persistent and severe. Without detailed observations before arrival, you're landing blind into potentially hostile conditions. All of these unknowns mean you need to bring equipment and supplies to handle a wide range of scenarios. That means more mass again, habitat modules that can withstand extreme temperatures and weather, rovers and exploration equipment, mining and manufacturing equipment to extract and process local resources, power systems, probably nuclear reactors, since you can't rely on solar panels if the planet has thick cloud cover or you're in the twilight zone. The concept of in-situ resource utilization, or ISRU, is key to making interstellar colonization viable. You can't bring everything you'll ever need from Earth. The mass would be prohibitive. Instead, you need to manufacture what you need from local materials. On Mars, proposed ISRU technologies include extracting water from ice deposits, splitting it into hydrogen and oxygen for rocket fuel and breathing air, and processing atmospheric carbon dioxide to produce methane and other chemicals. Building materials could be manufactured from Martian regolith, the loose soil and rock on the surface, using techniques like sintering, where material is heated and compressed into solid bricks without melting. On Proxima b, you'd need similar capabilities, but adapted to whatever resources are available. If there's water ice, that's invaluable. Water is essential for life support and can be split into hydrogen and oxygen. If there are metal-rich ores, you can smelt them into structural materials. If there's carbon, you can synthesize organic compounds. But Israel requires heavy industrial equipment, excavators, drills, furnaces, chemical processing plants, 3D printers or fabrication machines to turn raw materials into useful products. You need power to run all this, lots of it. You need skilled operators and engineers who can troubleshoot when equipment breaks down, which it inevitably will. You're essentially establishing an industrial base on an alien world with no supply lines, no outside support, and limited resources. It's like the early European colonies in the Americas, except instead of being months away by sailing ship from home, you're years away at light speed. There's no sending back for reinforcements or supplies. You succeed with what you have. or you fail. The psychological pressure of that reality is immense. Every decision carries weight. Mistakes can be fatal, not just to individuals, but to the entire colony. There's no margin for error, no safety net. And speaking of colonies, let's address the question of why. Why go through all this trouble, expense, risk, and suffering to reach another star system? The usual answers involve survival of the species. Earth faces existential risks. Asteroid impacts, supervolcanic eruptions, climate change, nuclear war, pandemics, artificial intelligence gone wrong, or threats we haven't even imagined. Establishing human populations on other worlds means that no single catastrophe can extinguish humanity. We become a multi-planet, eventually multi-star species, resilient against extinction. There's also the drive to explore, the same impulse that sent humans out of Africa to populate every continent, cross oceans, climb mountains, and eventually reach space. It's part of what makes us human. We want to see what's over the next hill, across the next ocean, around the next star. Scientific knowledge is another motivation. Studying another star system up close, potentially finding alien life, understanding planetary formation and evolution in a different environment, all of this advances human knowledge in ways that remote observations never could. Qual acquisition is sometimes mentioned, though it's hard to justify economically. Anything you could mine from Proxima b or the Alpha Centauri system could probably be obtained more easily from asteroids or moons within our own solar system. The energy cost and time delay make interstellar resource extraction impractical unless you're establishing permanent colonies that use those resources locally. Philosophical and existential reasons matter too. Some argue that humanity has a destiny or responsibility to spread life and consciousness throughout the galaxy. Others see it as the ultimate expression of human potential, proving we can overcome any challenge. But here's the uncomfortable truth. None of these reasons necessarily justify the costs and risks to the individuals making the journey. The species might benefit from having colonies on other worlds, but the crew and colonists endure decades of hardship, danger, and isolation. Many might die without ever seeing the destination. Their children, born in transit, have no choice in the matter. Is it ethical to commit people to multi-generational journeys? Can the first generation consent on behalf of their descendants who will be born into a situation they didn't choose? These are profound questions without clear answers. Different ethical frameworks give different responses. Utilitarian ethics might justify the mission if the long-term benefit to humanity outweighs the suffering of the participants. Deontological ethics might question whether it's ever acceptable to use people as means to an end, even a noble one. Virtue ethics might focus on the character and motivations of those who choose to go, emphasizing courage, sacrifice, and the pursuit of excellence. Religious and spiritual perspectives vary widely. Some traditions might view interstellar colonization as fulfilling a divine mandate to steward creation and spread life. Others might see it as hubris, humans overreaching their proper place. Still others might view it as irrelevant to spiritual concerns, a matter of practical decision-making with no inherent moral dimension. Individual motivations for volunteering would vary. Some might be driven by adventure and curiosity, others by a sense of duty or the desire to contribute to something greater than themselves. Some might be fleeing problems on Earth, seeing the mission as a fresh start. Others might be motivated by fame, the chance to be remembered as pioneers, but motivation can't erase the reality of what they'll face. Even the most committed and mentally prepared individuals will struggle with the isolation, confinement, and stress of interstellar travel. Let's talk about what happens when you finally arrive. After 43 years of travel, Proxima Centauri grows from a distant star to a blazing sun. Proxima b becomes visible as a disk, not just a point of light. You're approaching your destination, But your problems aren't over. In some ways, they're just beginning. You're traveling at 10% the speed of light, 30,000 kilometers per second. You need to slow down, or you'll shoot right past the Alpha Centauri system and continue into interstellar space. On the other side, your decades-long journey wasted. Slowing down requires just as much energy as speeding up. Remember our earlier calculation. Accelerating our 1,000-ton spacecraft to 10% light speed required about 4.5 times 10 to the 17 joules. Decelerating requires the same amount of energy. If you've been coasting for most of the journey to conserve fuel, you now need to flip your spacecraft around and fire your engines in the opposite direction, using thrust to fight against your forward momentum. If you're using a nuclear fusion rocket that achieved 1% light speed per year acceleration during the initial boost, deceleration takes just as long, 10 years of continuous thrust to bring you to a stop relative to Alpha Centauri. That means you need to carry enough fuel, not just for acceleration, but for deceleration too. Double the fuel requirement, double the mass, which means you actually need even more fuel to accelerate that additional fuel mass. The tyranny of the rocket equation strikes again. Alternative deceleration methods exist in theory. A magnetic sail, or mag sail, could interact with the interstellar magnetic field or the stellar wind from Proxima Centauri, creating drag that gradually slows you down. This uses no fuel, but it requires deploying an enormous superconducting loop, potentially hundreds of kilometers in diameter, and the deceleration is gradual, requiring decades of braking to shed your velocity. An even more speculative concept is the Bussard ramjet we mentioned earlier, which could theoretically reverse its operation, using magnetic fields to scoop up interstellar medium and expel it forward rather than backward, creating reverse thrust. But the engineering challenges are immense, and the technique has never been tested even in principle. Gravitational assists, or gravity slingshots, can alter a spacecraft's velocity by passing close to a planet or star, stealing a tiny bit of orbital energy. We use this routinely for solar system missions. The Voyager probes used gravity assists from Jupiter and Saturn to boost their speeds and alter their trajectories. Could you use Alpha Centauri A or B for a gravity assist to slow down? In principle, yes, but the geometry is tricky. You'd need to approach at exactly the right angle and distance, and the stars' positions in their mutual orbit would need to align with your arrival time. Given that your journey takes decades and your ability to adjust course is limited by fuel, threading that needle is extremely difficult. Even if you manage it, gravity assists don't eliminate velocity, they redirect it. You'd still be moving very fast relative to Proxima after the assist, just in a different direction. You'd need additional braking. Perhaps the most elegant solution is a laser-pushed light sail for acceleration, combined with a separate braking sail deployed near the destination. The braking sail would be designed to catch laser light beamed from a station in the Alpha Centauri system, but of course there's no station there when you arrive on the first mission. Catch-22, unless you send robotic probes ahead. A small probe, perhaps weighing only a few kilograms, could be accelerated to much higher speeds than a crewed ship, arriving years or decades earlier. It establishes infrastructure, a laser array powered by solar panels or a nuclear reactor, communication relays, survey satellites around Proxima b, maybe even automated mining and manufacturing equipment. By the time the crewed ship arrives, the groundwork is laid. The laser array is operational and can decelerate the ship's light sail. Survey data tells the crew exactly what they're arriving to. Perhaps robotic systems have even begun constructing habitats or extracting resources. This multi-phase approach is more realistic than a single crewed mission launching into the unknown, but it extends the timeline and multiplies costs. The robotic probe missions must be launched first, and you wait for them to reach the destination, send back data, and establish infrastructure before sending humans. Add another decade or two to the project timeline, and robotic probes aren't guaranteed to succeed. They might malfunction, crash, or encounter unexpected conditions that prevent them from completing their tasks. You might send humans based on reports from probes that later fail, leaving the crew without the infrastructure they were counting on. Let's assume everything works. Your ship decelerates successfully and enters orbit around Proxima Centauri or Proxima b. You've made it. After 43 years of travel, countless challenges overcome, perhaps lives lost along the way, you're here. Now what? Your first priority is detailed reconnaissance. Even if robotic probes have surveyed the system, human scientists can conduct more thorough investigations. You deploy satellites, send down landers and rovers, analyze atmospheric composition, map the surface, search for water, minerals, and any signs of life. If Proxima b is habitable, or at least survivable with technology, you begin landing operations. This is enormously risky. Landing on an unknown world with uncertain atmospheric conditions, weather, and terrain is dangerous. You're relying on sensor data and remote observations, but there's always the possibility of unforeseen hazards. Your landers need to be robust and reliable. They need heat shields if entering an atmosphere, parachutes or retro rockets for descent, landing gear that can handle uncertain terrain. You need life support systems that function independently of the orbiting ship, communication systems to maintain contact, power systems, probably radioisotope thermoelectric generators or small reactors. The first landing is probably unmanned, or perhaps carries a small crew who will return to orbit after initial surveys. Eventually, if conditions permit, you establish a permanent surface base. This base is your foothold on a new world. It starts small, inflatable habitats or rigid modules, similar to those on the International Space Station, but designed for planetary gravity and atmospheric pressure differences. Life support systems recycling air and water, power generation, likely nuclear given the uncertain solar environment, storage for supplies brought from the ship. Over time, if the colony succeeds, you expand. You begin ISRU operations, mining local materials and manufacturing what you need. You grow food in greenhouses or underground farms, reducing dependence on ship-based supplies. You explore further from the initial base, establish outposts, maybe even settle different regions if the planet is large and varied, but every step is fraught with danger. Equipment breaks down, people get injured or sick, resources run low. Conflicts arise over decisions and priorities. There's no resupply from Earth, no rescue if things go catastrophically wrong. You're truly on your own, and you're living with the constant awareness that Earth is over 4 light-years away. Messages take years to arrive. The people you left behind, assuming any are still alive after 4 decades, are living in a world that's moved on without you. Technology has advanced, politics have shifted, culture has evolved. You and Earth are diverging, becoming separate branches of humanity. This divergence accelerates over generations. Children born on Proxima b have never seen Earth. To them, it's a myth, a historical curiosity. Their identity is tied to this new world, not the old one. Language begins to drift, developing new words for local phenomena and experiences. Cultural practices evolve differently under different environmental pressures. Eventually, the Proxima colony might not consider itself human in the same way Earth humans do. They're adapted to different gravity, different light, different atmospheric composition if genetic engineering or long-term evolutionary pressure changes them. They might develop new social structures, new philosophies, new ways of understanding the universe. This is both beautiful and unsettling. You've successfully spread humanity to another star, achieving something profound, but you've also created the conditions for human divergence, possibly even speciation over enough time. The galaxy might one day be home to many branches of humanity, each adapted to its world, each developing in isolation. Or perhaps faster-than-light communication is discovered, keeping distant colonies in close contact. Or perhaps interstellar travel becomes routine, frequent enough that populations mix and exchange genes, ideas, and culture. But with our current understanding of physics, those outcomes seem unlikely. Let's circle back to the fundamental question: is this worth it? From a purely rational cost-benefit analysis, interstellar colonization is almost impossible to justify in the near term. The resources required could solve countless problems on Earth. The trillions of dollars needed to build and launch an interstellar mission could fund renewable energy infrastructure, carbon capture, pandemic prevention, poverty alleviation, education, and research across countless fields. Sending humans to Proxima Centauri doesn't feed hungry people on Earth. It doesn't stop wars or cure diseases or reverse environmental damage. In fact, diverting resources to interstellar missions might make Earth's problems worse by taking attention and funding away from immediate needs. But humans don't operate on purely rational cost-benefit analyses. We do things because they inspire us, because they challenge us, because they give meaning and purpose. The Apollo program cost about $25 billion in 1960s money, equivalent to roughly $250 billion today. Did it solve poverty or end the Cold War? No, but it advanced technology, inspired generations, and proved humans could accomplish seemingly impossible feats. Interstellar travel is the ultimate extension of that impulse. It's the most difficult thing humans could attempt, and difficulty is part of the point. We climb mountains not because they're useful, but because they're there, because the challenge calls to something deep in human nature. Still, there's a difference between climbing a mountain and committing generations of people to a journey they didn't choose. There's a difference between spending resources on inspiration and diverting them from urgent survival needs. Perhaps the answer is timing. Maybe interstellar missions make sense once humanity has solved its existential problems on Earth, created sustainable abundance, eliminated poverty and preventable disease, stabilized the climate, and built a thriving solar system civilization. At that point, with resources and technology far beyond what we have now, reaching for the stars becomes feasible without sacrificing the well-being of people left behind. Or perhaps crisis forces our hand. If Earth faces an imminent existential threat, asteroid impact, runaway climate change, nuclear war, a desperate attempt to preserve humanity on another world becomes the highest priority, regardless of cost. There's also the possibility that we never send humans at all. Perhaps we send our minds instead. Advanced artificial intelligence, if developed, could be far better suited to interstellar travel than biological humans. AI doesn't need life support, food, or water. It can survive radiation with proper shielding for electronics. It can be powered down during long coasting phases, consuming no energy. It can be backed up, copied, and transmitted as data. Imagine sending an AI probe to Proxima Centauri. It weighs far less than a crude ship, maybe only a few tons, including power systems, computers, sensors, and communication equipment. It accelerates to a significant fraction of light speed, perhaps 20 or 30%, making the journey in 15 to 20 years. Upon arrival, it surveys the system, gathers data, and transmits findings back to Earth. Perhaps it even begins constructing infrastructure using automated manufacturing, building a base that humans could later inhabit if they choose to make the journey. Or perhaps the AI is sophisticated enough to experience and appreciate the universe in ways comparable to humans. It explores not on our behalf, but for its own sake, a form of consciousness we created, now independent and spreading through the galaxy. This raises profound philosophical questions about consciousness, identity, and what it means to be human. If we send AI explorers instead of biological humans, have we really colonized the stars, or have we created successors who will inherit the galaxy while we remain on Earth? Some philosophers argue that consciousness is what matters, not the substrate it runs on. If an AI can think, feel, appreciate beauty, and make meaningful choices, then it's a worthy heir to humanity's exploratory legacy. Others insist that there's something irreplaceable about biological human experience, that embodiment, mortality, and our specific evolutionary history shape consciousness in ways that can't be replicated in silicon. These aren't just academic debates. They have real implications for how we approach space exploration and the future of our species. Do we invest in extending biological human life and adapting our bodies for space through genetic engineering, cybernetic enhancement, or life extension technologies? Or do we accept that our biological form is optimized for Earth and focus on creating artificial successors better suited to the cosmos? There's a middle path: uploaded consciousness. If we develop technology to scan and simulate a human brain in sufficient detail, we might be able to transfer human minds into digital substrates. You could upload yourself, your memories, personality, and consciousness into a computer that's then installed in a spacecraft. From your perspective, assuming the upload preserves continuity of consciousness, you'd still be you. You'd think and feel and experience, just in a digital environment rather than a biological body. You could survive the rigors of space travel that would kill your biological form. Radiation, vacuum, extreme temperatures, none of it would matter to your digital substrate with proper shielding and redundancy. The journey to Proxima Centauri could be experienced in virtual reality, time compressed or expanded as needed. You could slow your subjective experience during the decades of coasting, making the journey seem to pass quickly, or you could run faster than real time, living thousands of subjective years in the time it takes to cross interstellar space, learning, creating, and experiencing within simulated environments. Upon arrival, you could control robotic bodies to explore Proxima b physically, or you could remain digital, experiencing the system through sensors and simulations. You might even copy yourself, creating multiple instances that explore different areas simultaneously, later merging memories and experiences. This sounds like science fiction, and it is, for now. We have no idea if consciousness can be uploaded, if subjective experience would survive the process, or if the result would be you, or just a copy that thinks it's you while the original dies. The philosophical problem of personal identity haunts these concepts. If you're scanned and uploaded, but your biological body remains alive, which one is the real you? If you create copies of your uploaded mind, are they all you, or separate individuals? If you merge copied instances back together, combining different memories and experiences, what happens to the identity of each copy? These questions have been debated by philosophers for centuries in various forms. The ship of Theseus, which asks if a ship remains the same vessel after every plank is replaced. Teleportation paradoxes that question whether someone who is disintegrated and reassembled at another location is the same person, and thought experiments about brain transplants and duplicates. There are no universally accepted answers. Different philosophical traditions and individuals will draw different conclusions. But for interstellar travel, these questions become urgently practical if mind uploading becomes technologically feasible. Setting aside uploaded consciousness, let's consider another approach: sending genetic information rather than living humans. Your DNA is a compact information storage system. The entire human genome contains about 3 billion base pairs, which translates to roughly 750 megabytes of data when encoded digitally. You could transmit that information as a radio signal to a receiving station at Alpha Centauri. At light speed, the transmission takes 4.24 years. The receiving station, established by earlier robotic probes, uses the genetic information to synthesize DNA, construct cells, and grow human embryos through artificial wombs. Robotic systems raise the children, educating them with transmitted knowledge from Earth, creating a human colony without ever sending living humans across the void. This reduces mass dramatically. Instead of a 1,000-ton crewed spacecraft, you're sending radio signals and relatively small robotic infrastructure. The energy and resource requirements drop by orders of magnitude, but the ethical questions are staggering. You're creating human beings who will be raised by machines with no biological parents, no natural human community during their formative years. What does that do to psychological development? Can AI, no matter how sophisticated, provide the emotional bonding and social context that human children need? And these children didn't choose to be created in an alien environment. They're being brought into existence specifically to serve the purpose of colonizing Proxima b. Is that ethical? Do we have the right to create people for a purpose they didn't consent to? You could argue that no one consents to being born. All humans are brought into circumstances we didn't choose by parents who made decisions for us. But there's a difference between being born into an established human society on Earth and being created as part of an experimental colony on an alien world, raised by robots, with no possibility of escape or return. These concerns might be mitigated if the robotic systems are sophisticated enough to provide genuine care and education, if the children grow up healthy and happy, and if they eventually form their own community and reproduce naturally. But the initial generation faces unique psychological challenges that we can barely imagine. There's also the technical challenge of developing artificial wombs capable of gestating human embryos to full term, something we haven't yet achieved on Earth. Current research has successfully grown animal embryos in artificial environments for limited periods, but full gestation remains beyond our current capabilities. Even if we solve that, you need robotic systems capable of caring for infants and children through decades of development. Feeding, cleaning, protecting from danger, teaching language and social skills, providing emotional support. The AI and robotics required are extremely advanced, possibly requiring capabilities we won't develop for decades or longer. If you are still watching, please subscribe to the channel and give this video a like. You'll join a community of cosmic explorers diving deep into astronomy, astrophysics, and the grandest questions about our place in the cosmos. Now let's consider yet another approach: hybridization. Instead of sending fully biological humans or pure AI, send enhanced humans, cyborgs with biological brains and bodies augmented with technology to survive space travel. Cybernetic enhancements could include radiation-resistant skin grafts, organs bioengineered to function in variable gravity, neural interfaces that allow direct control of spacecraft systems, metabolic modifications to reduce food and oxygen requirements, and life extension treatments to survive the decades-long journey. This combines the benefits of both approaches. You retain human consciousness and experience in biological form, but you've adapted that form to survive conditions it wasn't evolved for. The enhanced humans are still human in some meaningful sense, but optimized for space. But where do you draw the line? How much can you modify a human before they're no longer human? If you replace organs with artificial versions, augment the brain with computer interfaces, alter genetics to handle radiation, extend lifespan by orders of magnitude, is the result still Homo sapiens or a new species? And there are social justice questions. Who gets enhanced? If enhancement is expensive, does it become available only to the wealthy, creating a class divide between enhanced space colonists and baseline humans remaining on Earth? Do nations compete to create enhanced populations, triggering a biological arms race? Regulation and international cooperation would be essential, but also extremely difficult to achieve. Nations and corporations might pursue enhancement technologies in secret to gain advantages. The potential for abuse is enormous. We're now deep into speculative territory, discussing technologies that don't yet exist and may never be developed. But that's inevitable when seriously considering interstellar travel. With current technology, it's barely conceivable. With foreseeable near-term technology, it's monumentally difficult, but perhaps achievable over centuries. With speculative far-future technology, it becomes more feasible but introduces ethical and philosophical complexities we're not prepared to address. Maybe the most honest answer is that we don't yet know how to reach the stars. Our understanding of physics, engineering, biology, and social organization isn't sufficient. We're like medieval scholars trying to plan a moon landing. We can imagine it, we can sketch rough ideas, but the actual knowledge and technology required are beyond our current grasp. That doesn't mean we shouldn't try. Progress happens through incremental steps. We start by establishing sustainable presence in low Earth orbit, which we've done with the International Space Station. We return to the Moon and establish permanent bases, learning to live and work off-world for extended periods. We send humans to Mars, dealing with the challenges of longer duration missions and more distant operations. Each step teaches us lessons applicable to the next. Technologies developed for near-Earth operations mature and become ready for more ambitious missions. Closed-loop life support systems improve, radiation shielding advances, propulsion systems evolve, medical understanding of space adaptation deepens over decades or centuries. Interstellar missions might transition from impossible to merely extremely difficult to eventually routine, at least on the timescales civilizations operate on. But there's a darker possibility. Maybe interstellar colonization is fundamentally impractical, and we never do it. The distances are just too vast, the energy requirements too enormous, the challenges too severe. Despite advances in technology, the basic physics of crossing light years of space never becomes easy enough to justify the cost and risk. Humanity remains confined to our solar system indefinitely. This wouldn't necessarily be a failure. Our solar system contains vast resources and living space if we learn to utilize them. The asteroid belt contains metals, minerals, and volatiles worth quintillions of dollars. The moons of Jupiter and Saturn have water ice, organic compounds, and potential habitats beneath icy surfaces. Even constructed habitats in space, O'Neill cylinders and Stanford toruses, could house billions or trillions of people in Earth-like conditions. A solar system civilization could thrive for millions or billions of years without ever leaving. We could build Dyson swarms, networks of solar collectors capturing most of the sun's energy output, providing almost limitless power for industry and habitation. We could engage in megascale engineering projects that dwarf anything planetary civilizations could achieve, and we could still explore the galaxy through robotic probes and observation. Telescopes improve constantly. Future instruments might image exoplanets directly, studying their atmospheres, weather, and even surface features in detail. We might detect signs of life, or even technological civilizations, through biosignatures in atmospheric spectra or technosignatures like artificial lights or megastructures. Communication with other civilizations, if they exist, could happen across interstellar distances without physical travel. At light speed, messages take years to cross between stars, but patient civilizations could maintain dialogues across centuries, exchanging knowledge, culture, and philosophy. Perhaps that's the real future. A galaxy of stay-at-home civilizations, each thriving in its own star system, communicating but never meeting face-to-face. It's not the vision of space exploration popularized by science fiction. with starships crossing the galaxy and humans settling thousands of worlds, but it might be realistic given the constraints of physics. Or perhaps we're simply not imaginative enough. Technologies we can't currently conceive might make interstellar travel trivial. Wormholes, if they can be created and stabilized, could connect distant points in space instantaneously. Alcubierre drives or other space-time manipulation schemes could allow effective faster-than-light travel without violating relativity. Quantum teleportation might eventually be scaled up to macroscopic objects, allowing instantaneous transmission of matter across any distance. These concepts are highly speculative, and most physicists are skeptical they'll ever be practical. They require exotic forms of matter and energy we've never observed and may not exist. They might violate fundamental principles we don't yet understand, but dismissing them entirely would be premature. Physics has surprised us before. 1,000 years ago, human flight seemed impossible. 500 years ago, space travel was inconceivable. 100 years ago, nuclear energy was theoretical curiosity. 50 years ago, the internet didn't exist in any practical form. 20 years ago, smartphones were primitive. Today, we're editing genes, building quantum computers, and creating artificial intelligence. Extrapolating technological progress is dangerous because it's non-linear and unpredictable. But it's equally dangerous to assume our current understanding represents fundamental limits. Every generation thinks it's approaching the boundaries of what's possible, and every generation is proven wrong. So maybe interstellar travel will be solved by physics we haven't discovered yet, using principles we don't currently understand. Maybe your descendants, whether biological, digital, or something we can't yet imagine, will look back at our struggles with chemical rockets and nuclear propulsion the way we look at sailing ships and steam engines, quaint, primitive, endearing in their limitations. Or maybe the universe is genuinely vast and empty in ways that keep civilizations isolated. Maybe the speed of light is a true insurmountable barrier, and the galaxy will forever be a lonely place where countless civilizations arise, flourish, and die without ever meeting. We don't know. And that uncertainty is both frustrating and beautiful. Let me bring this full circle back to your original question. How do you travel to another star? The honest answer is, with extreme difficulty, enormous cost, unprecedented cooperation, revolutionary technology, and acceptance of risks and timeframes beyond anything humanity has attempted. You need propulsion systems orders of magnitude beyond our current capabilities. You need life support that can sustain humans for decades or generations. You need radiation shielding, navigation systems, power generation, communication across light years, psychological support for crew facing isolation and confinement, redundancy and repair capabilities with no external support, and landing systems for an unknown world. You need to solve engineering challenges, biological challenges, psychological challenges, social challenges, and ethical challenges simultaneously. You need funding that dwarfs the largest projects in human history. You need international cooperation lasting longer than most nations have existed. You need patience measured in centuries. And even if you solve all of that, you're sending people on a journey many won't survive, to a destination that might not be habitable, with no possibility of return, to establish a colony that will diverge from humanity and face challenges we can barely imagine. Is it impossible? No, the physics allows it. The engineering is conceivable, if incredibly advanced. The resources exist in principle. Is it practical with current technology? Absolutely not. We're centuries away from having the capabilities required, at minimum. Will we ever do it? That depends on us. It depends on whether we survive our current challenges as a species. It depends on whether we develop the technology and social organization required. It depends on whether we decide it's worth the cost. It depends on whether something compels us to try, either inspiration or desperation. Maybe in a few hundred years your descendants will board a spacecraft bound for Proxima Centauri or another nearby star. Maybe they'll be biological humans, enhanced cyborgs, uploaded minds, or something entirely different. Maybe they'll use propulsion systems we haven't imagined yet. Maybe the journey will take decades, or maybe they'll have solved faster than light travel. Or maybe humanity will thrive in our solar system for millions of years without ever leaving, content to explore the universe through telescopes and radio signals, building a magnificent civilization in the space around our sun. Or maybe we'll destroy ourselves before we have the chance to find out, victims of our own short-sightedness, conflicts, or inability to manage powerful technologies responsibly. The future isn't written. Interstellar travel remains one of the grandest challenges we can conceive, a goal that tests the absolute limits of human capability and ambition. Whether we achieve it depends on choices we make now and in the coming centuries. What I can tell you with certainty is this: the stars are far away, unimaginably far. The universe is vast beyond human comprehension. The challenges of crossing even the smallest interstellar distances are staggering. But humans have always looked up at the stars and wondered. We've always pushed against our limits. We've always dreamed of reaching beyond our current grasp. Maybe that's enough. Maybe the dream itself, the aspiration to reach the stars even if we never quite manage it, drives us to become better, smarter, more capable. Maybe the journey toward interstellar capability is more important than the destination. Or maybe someday, someone will stand on the surface of Proxima Centauri b, looking up at an alien sky, and remember that it all started with people like you, Josue, asking how we get there. That's the real answer to your question. We get there by asking, by imagining, by learning, by pushing the boundaries of what's possible. We get there one incremental step at a time, over generations, through the accumulated effort of millions of people solving millions of problems. We get there by refusing to accept that the stars are unreachable, or we don't get there at all, and that's okay too. The universe is beautiful whether we visit other stars or simply appreciate them from Earth. The value is in the striving, the dreaming, the reaching for something beyond ourselves. So how do you travel to another star? One step at a time, over centuries, with courage, ingenuity, cooperation and hope, and maybe, just maybe, a little bit of stubbornness in refusing to accept that anything is truly impossible. Interstellar travel sits at the intersection of physics, engineering, biology, psychology, ethics and philosophy. It's not just a technical problem, but a challenge to everything we are as a species. The question you asked opens up entire fields of study: astrodynamics, propulsion physics, life support engineering, radiation biology, space psychology, planetary science, astrobiology, ethics of space colonization, and more. Each aspect I've discussed could be expanded into multiple books. Entire careers are devoted to small pieces of the interstellar travel puzzle. What I've given you is an overview touching on major challenges and proposed solutions, but every topic goes far deeper. If this journey through the challenges and possibilities of interstellar travel has sparked your curiosity, there are countless directions to explore further. You could study the physics of propulsion systems, the biology of long-duration spaceflight, the engineering of closed-loop life support, the psychology of isolation and confinement, or the ethics of space colonization. Or you could simply look up at the night sky, find Alpha Centauri if you're in the southern hemisphere or low northern latitudes, and contemplate what it would take to reach those distant points of light. The stars are waiting. Whether we ever reach them is up to us. Surviving the journey is only half the battle. You're not coming back home ever. Click the video on screen to discover the real reason interstellar travel is a one-way trip. The physics of return journeys will blow your mind. Trust me, it's not what you think.